Hello everyone, this is Bo from Beijing Normal University, and I am very excited to share our paper, Noise Diffusion for Enhancing Semantic Faithfulness in Text-to-Image Synthesis. First, let me briefly introduce the background of our paper. Although diffusion models have been very successful, there are still some challenges in ensuring precise alignment between text and images. And previous works have found the alignment highly depends on the initial noisy latent. And the existing methods based on attention maps to optimize the noisy latent cannot capture and analyze the complicated semantic information contained in the prompt. So in this paper, we propose a novel method to optimize the noisy latent. First, we introduced the large vision language model to calculate the VQ score of generated images. And the VQ score is used to adjust the step size for updating the noisy latent. Then we select a set of noises in the Gaussian space, and we calculate the step difference corresponding to each noise. And then we select the noise with the maximum value of the inner product of the gradient and the step difference divided by the square of the L2 norm of the step difference. And then we use the forward diffusion process to optimize the noisy latent. We can have a feasibility analysis about our method, since the VQ score has bounded second-order derivative almost everywhere. So if the value of the inner product divided by the square of the L2 norm is large enough, we can obtain a new latent with a higher VQ score. Another issue is the gradient computation. The computational cost will be extremely high if we include the entire denoising process in the backward propagation. So we simplify this process by regarding these following terms as zero. Okay, then it comes to the experimental section of our paper. We introduce simple cases and complex cases. For simple cases, we use dataset animal and object, which is a mainstream prompt dataset, and we introduce position information to the simple cases and it forms the complex cases. For each prompt, we use 25 randomly selected Cs, and we use VQ score and clip score to evaluate the faithfulness of generated images. Epoch 0 refers to the value of vanilla stable diffusion models, and the dotted lines refers to the values of initno, which is the competitive baseline method in our paper. And we can see when the epoch increases, the VQ score increases aggressively, and the clip score also increases aggressively, and they both exceed the values of initno. For qualitative results, we can see from both the simple cases and the complex cases. We can get the conclusion that our method has a greater capacity to recognize the details of the objects. Another important discussion is whether the optimization technique proposed in our paper is effective. So we compare our method with several other different optimization techniques. The first two lines, PGD and mean variance, refer to traditional methods that directly perturb the latent, and random sampling refers to randomly selecting a noise in the Gaussian space. And random diffusion refers that we use the strategy that the step size is determined by the VQ score, but we don't use gradient information to select the noise. Yeah, from the result, we can see that if the initial noise is too far from the ideal region, the traditional methods don't work. And if the ideal region is too small, randomly sampling the noise from the Gaussian space is also ineffective. Comparing random sampling with random diffusion, we can see the strategy that using the VQ score to determine the step size is very effective. And comparing random diffusion with noise diffusion, we can see utilizing gradient information to select noise can accelerate convergence. And finally, we conduct ablation study on the impact of models. We use 2 prompts to represent simple cases and complex cases respectively. And we can see from the results that the different vision language models lead to consistent improvements of the generated images by the various stable diffusion models. So we can see that our method is very adaptable. Okay, that's all about our paper. The code is available at GitHub. You can also scan the QR code to learn more about our project. Thank you so much.